my pleasure to introduce our next speaker, Guiseppina Barbieri, the University of Salerno. And the title of her talk is From Sets to S Sets. So, please.
Everybody, first of all, I would like to thank the organizing committee for giving me this opportunity. And the title is From Sets to S Sets, but maybe the title should be The Fundamental Theorem of Calculus in the Real Line to the History. Okay, the theorem, very well known, is this, contained also in the book by Cauchy, written in 1831, the first version. And okay, if f is differentiable of an interval, then the definite integral of its derivative equals this difference. And it is very, okay, I must approach the microphone. And it is also very well known that in the case of Riemann integration, it is necessary to add the additional condition that the function must be Riemann integrable. This condition is necessary because not every derivative turns out to be Riemann integrable. And here is a well-known example of a function which is differentiable everywhere on the real unit interval, but its derivative is not Riemann integrable since it is unbounded, and it is neither Lebesgue integrable since f is not absolutely continuous on the real unit interval. Therefore, as it is well known, the Lebesgue integral as well as the Riemann integral does not solve the problem of primitives. Well, the problem of primitives is the problem of recovering the function from its derivative. It has the problem of whether every derivative is integrable. And as it is also well known, the Lebesgue integral solves the problem of primitives in the frame of bounding function, but it does not completely solve the problem of primitives for unbounded function, and the previous example has been done by Lebesgue himself. But the history continues, and the first solution to this problem was given 10 years after Lebesgue's thesis by Arnaud Denjoy in 1912, and he was followed by Oscar Perron in 1940, who was inspired by a characterization of the Lebesgue integral function given by Charles-Jean Barrault de la Volée-Poussin. Both definitions are constructive. Denjoy developed a very, very complicated new method of integration called totalization that includes the Lebesgue integral and that gets the value of the integral of a function through a transfinite process of Lebesgue integration, limit operation, very, very complicated. Perron used instead an approach that does not require measure theory, and it is based on families of major and minor functions, the so-called overfunction and underfunctions. And later on, Hayek, Alexandrov, Luhmann independently proved that the Denjoy integral and the Perron integral are equivalent, and indeed now it is called the integral of Denjoy-Perron. But only using make this definition understandable, and he introduced the following notion of absolutely continuous in the strict sense, AC star, and generalized absolutely continuous in the strict sense. And this definition is based on the oscillation, which is supreme. Okay, we can read a function is said to be absolutely continuous if the sum of oscillations is smaller for each finite system of non-enveloping intervals with these two properties. And a function is said to be generalized absolutely continuous on an interval if it is continuous and there is a decomposition of the regional interval as the union of closed sets such that the restriction of F to EI for each I is absolutely continuous in the strict sense. And okay, so using was able to prove the following characterization of the Danjois-Perron integrable function. A function is Danjois-Perron integrable if and only if there is another function, capital F, which is generalized absolutely continuous in the strict sense on the interval, which is differentiable almost everywhere for Lebesgue measures on this interval, and such that derivative coincide with the original function almost everywhere on the interval. Okay, just remarks. The if part of this characterization is often called the descriptive definition of the Danjois-Perron integral, and since the constructive definition of the Danjois-Perron integral was not immediate as that of the Riemann integral, only a few mathematicians were interested in working with it. So this descriptive definition became the most known definition of the Danjois-Perron integral. And another remark, in contrast to the Riemann and Lebesgue cases, if F is the Danjois-Perron integrable over interval, its absolute value needs not to be the Danjois-Perron integrable, and the Lebesgue integrable functions are exactly the ones which are Danjois-Perron integrable together with the absolute value. Okay, so in spite of the general conviction that no modification of Riemann method could possibly give such powerful result as that of Lebesgue integral, Kurzweil and Ansdorf introduced independently a general version of the Riemann integral that now is known as the Ansdorf-Kurzweil integral, and such an integral solves the problem of primitives and includes the Lebesgue integral, of course, in the sense that if a function is Lebesgue integrable, it is also integrable in the sense of Ansdorf-Kurzweil, and the two integrals coincide. Okay, and now we are going to give the exact definition of Ansdorf-Kurzweil integral. We need as an ingredient a gauge. A gauge is simply any positive function defined on an interval. We need a tagged partition, which is any collection of pairwise disjoint intervals with points arbitrarily chosen inside AI, such that the intervals is the union, and the key ingredient. The key ingredient is a delta affine partition. Too high. Okay, is delta affine partition. Whenever P is said to be delta affine, whenever AI is contained in this interval xi minus delta xi, xi plus delta xi for every I. And the last ingredient is the Riemann sum of F with respect to partition, which is defined in this way, where lambda is the Lebesgue measure. Okay, yes, a remark. Given any positive constant delta, it is always possible to construct a tagged partition which is delta affine, or as mesh size smaller or equal to delta. But in the case of an arbitrary non-constant gauge, delta, the question is more delicate, and the existence of delta affine tagged partition has to be proved. And this was already done in 1895 by Pierre Cousin, and here is the Cousin's lemma, which is equivalent to the classical Borel-Lebesgue property. Okay, and now the exact definition of Kurzweil integrable function. Okay, a function is said to be Kurzweil integrable if it is possible to approximate the number, the integral with delta fine partition P. And okay, this number I, real number I, is called Kurzweil integral on AB. It is denoted by this symbol HK, stands for Kurzweil. Okay, yeah, other remark, easy remark. The restriction of the Kurzweil definition to constant gauges just give the Riemann integral. The fundamental idea in their definition is to force the step to be smaller around points where the function is discontinuous or tends to infinity. And this idea, which is familiar to numerical analysts, was already mentioned by Euler. And this is contained in a very beautiful paper by Jean Moulin, to history of integration theory, Riemannesque versus Romanesque. And here is what Euler wrote in 1768. We can read these lines. Okay, we already have noticed that the intervals aj minus aj minus 1, that x is assumed to go true, must be taken very small in such a way the corresponding values f on aj minus 1 and f on aj do not differ too much one from the other. From this, one must decide if the intervals must be taken equal or unequal. Indeed, where the value of fx does not change too much when x varies, the interval in which x moves can be taken larger without danger. On the other hand, in places where small changes of x lead to violent variation of fx, one will have to take the interval very small. Okay. Well, yeah, the Kurzweil integral is equivalent to the Draper integral, and this result was shown by several mathematicians by proving the following characterization of the Kurzweil primitives. The family of all Kurzweil primitives coincide with the class of generalized absolutely continuous function, as used in proof. The Kurzweil definition has been adopted to introduce integral calculus in many monographs, and it is taught to undergraduate students in mathematics and physics sometimes. In Italy, I don't know in other countries. Okay. But now we come to assets, where an asset is for us a subset of the real line whenever the S-dimensional exterior Hausdorff measure is, which is defined in that way, supremum of infimum of these countable sums to the power of S, whenever E is included in this countable union with diameter less than delta, and S is strictly greater than 0 and strictly less than 1. This is actually a measure of Borel sets. And okay, so from now on, E is a closed S set, and we have to generalize to this setting, which is an interval. An interval is simply an intersection of the classical interval with this closed S set, and a tethered partition now is a finite collection of pairwise disjoint E intervals tilde I and point xi inside these E intervals. Okay, we have to generalize to this setting, to this framework, the Riemann sum, and we have the notion of S Riemann sum related to a partition P, but it simply substitutes the Labelle measure with this X Hausdorff measure. And of course, the intervals with these E intervals, and xi inside these E intervals. In this way, we can give this notion of S-Riemann interval, which is, okay, we can read a number. If there exists a real number I, such that for every epsilon there is a delta, such that this difference is more for each partition, such that the S exterior out of measure is more than delta, and the number I is called S-Riemann integral of F on E. Incidentally, there are a huge literature on these S-Riemann interval. Scholars like Chinese scholars Jiang Su and Indians scholars like Parvati Jangar introduced an extension of the Riemann integral, which is up to a constant exactly this S-Riemann integral. And okay, and now we need also a derivative in this setting, the S derivatives, and we use a definition introduced by three Spanish men, three Miguel de Guzman, Miguel Martin, Miguel Reyes. And here is the definition of left derivatives and right derivatives as the limit from the right and from the left of the incremental ratio. And the novel is that the xx0 is defined thanks to S Hausdorff measure. And okay, as usual, we say that the S derivative exists if the left derivatives and right derivatives coincide, and here is the paper by de Guzman, Martin, Reyes, published in 1990. Okay, but now our aim is to look for the best version of an integral in this setting for the fundamental theorem for solve the problem of primitives. And as Riemann integral is not a right integral because we have an example of a function defined on the ternary counter set such that its derivative, S derivative, whereas is the dimension of a counter set logarithm of 2 to the base of 3, is a null function, so the S Riemann integral is null, but of course this difference F on 1 is 1, so 1. It does not solve, does not hold the fundamental theorem of calculus. And hence, a generalized an extension of a Kurzweil integral on this setting to this setting can be done, and of course, exactly as in the classical case, we can we say that the function is Ansatz Kurzweil interval if we can approximate with the delta affine partition now with elements are E intervals. Okay, the peculiarity of the SH integral with respect to S Riemann integral is that, of course, the SH integral allows to neglect the value of the S Riemann sum related to some partition containing big intervals in proximity of very bad points. Okay, here is the comparison, of course. We have for S Riemann integral involves S Riemann sum related to partition whenever HS, the S exterior Hausdorff measures is less than delta for some appropriate constant. Instead, for SHA integrals involves the S Riemann sum related to all partitions satisfying this inequality where there is delta on X-side gauge for some appropriate gauge, and okay, and a choice of Xi inside E intervals. Okay, another remark. If F is an SH interval function, but it is not S Riemann interval, then of course this infimum must be 0 for each gauge. Otherwise, by way of contradiction, if we have that infimum equals delta, then that delta does the work in order to for Bayes F S-Riemann integral. Oh, okay, simply remark. Okay, and now our aim to solve the problem of primitives for S sets. We had an idea. The idea was what happens? What does it happen if we use an integral in which the gauge is a positive constant, which is easier to handle, but the choice of points is not arbitrary in the interval, say I, but must satisfy some constraints. And to define this quite general integral, we adapt an idea from, by Dergy and Evans for function defined on ST. And okay, so consider a countable dense subset gamma of V. We call this countable dense subset a trajectory. Restrict our attention only to the S-Riemann sum related to all partitions such that S out of measure is less than delta for some appropriate constant, but such that xi is not arbitrarily chosen inside tilde ai, but is the first element of gamma that belongs to tilde ai for every I. Okay, the idea of first return type goes back to Poincaré's first return map of differentiable dynamics. It was already used in differential theory and integration theory, and I mentioned two papers by Maley, published in 1992, and by Freiling, appeared in 2000. Okay, yes, here. It is the exact definition of our S first return integrable function with respect to trajectory, where trajectory is any sequence of distinct points of the S-closed set density. And okay, we approximate with the partition such that the S out of measure is less than delta, and xi, as said before, is the first element of gamma that belongs to tilde I. Okay, we have some result. The S first return integral includes the Lebesgue integral with respect to the S out of measure. There exists a non-S Riemann integrable function which is not S first return integrable, but this idea, okay, I would like to skip for the last slide. Our idea to find the best version of integral in this framework in order to solve the problems of primitives. Integration is a reverse operation with respect to differentiation is a bad idea because we find a function which is an S derivative, but f is not S first return integral. So our attempt is a failure in some sense, and we can say that since there are S derivatives not as first return interval, we can conclude that in order to obtain the best version of the fundamental theorem of calculus on S sets, exactly as in the real line in the classical case, we need to consider Ernst-Kurzweil type integral. It has an integral in which the gauge is not a constant. And these results are contained in a recent paper written jointly with my friend Donatella Bongiorno from University of Palermo and Alireza Khalili Golmakane from Iran. Okay, many thanks for your listening. That's all.
Thank you very much. Questions, remarks?
Thank you. My question is if there are some additional problems in a multi-dimensional case. For example, what's going on with Stokes theorem, Gauss theorem? So you always talked about the one-dimensional situation. Yeah. If there are some results in the multi-dimensional. Okay, thank you.
Thank you. Any other question or remark?
Thank you. Are there still problems that you cannot solve, and what could be the next step in generalization? Thank you.
As a disclaimer, yeah. As a disclaimer, this is not exactly my research topic. My friend involved me in this research topic, and we studied this aspect. Maybe, yes, there are many questions that can be developed in this field. Okay, yes.
Thanks. Any other question, comment? I must say the same thing, that thanks in two ways for the time that you gave and for your very nice talk. Thank you.